forse. Sì. No. Mi piace. Allora, proviamo a staccarlo. Secondo me adesso lui si è arrabbiato. Sì, no, ma funziona. Secondo me si è arrabbiato perché era chiuso. Era no, ha detto che non riprende. Technical problem. Reboot.
The time is going to be subtracted by your presentation.
No, dopo ritorno. No, sì, aspetta, perché l'abbiamo chiuso, no? E poi sono chiuso. Vabbè, adesso mi riapre tutto il mondo. Ecco. Ci siamo qua? Sì. Va bene, luci.
Okay, Maria Rosa, please.
Pronti? Okay. Okay, thank you very much for an extra minute of patience. And the first thing I'd like to do is to thank the organizer for giving me this opportunity to be here. It's a great pleasure to be here in this special occasion and also to present to you the BMC survey, even if you already know everything about it, since it has been going on for quite some time. This is the effort of a moderate team of astronomers, and especially here in Naples, we have a group working on the variable stars, on the Cepheids, and you'll see in the audience Vincenzo Ripepi and Marcella Marconi. And together with this team, a great thank, of course, goes to the CASU and the Whitefield Astronomy Unit in Edinburgh, because without them, none of this would be possible, because they are reducing our data and making them available to us and also to the community together with ESO. Wrong way, this way. Okay, so to recap, what is the BMC survey? This is the VISTA survey of the Magellanic Cloud system. It's a near-infrared imaging survey in 3 bands, Y, J, and KS. And it is a deep survey compared to many other surveys of the Magellanic Clouds, because it aims to go down to the main sequence turn-off. And also, it is a monitoring survey because we acquire multi-epoch, especially in the K-band, we have up to 12 epochs. And this is important to derive accurate magnitudes for variable stars and to measure the structure of the galaxy. So some of the parameters you're interested in, I knew this, okay, here. We reach a depth of 22 magnitudes in Vega system in almost the 3 bands. And it's a survey of about 2,000 hours, so it started late 2009, and as you saw from Magda this morning, it's up on track to finish in about 2018. This way, yes. So the 2 main science goals of the survey are to derive the spatially resolved star formation history for the galaxies, and we do that by interpreting color magnitude diagrams using theoretical models. And you will see in a minute what I mean about this. And the other goal is to derive the structure of the galaxies also in 3D, so really to measure the depth of the Magellanic Clouds And normally what we expect is a depth of a few kiloparsec for the large cloud and up to 20 kiloparsec for the small cloud. And translated in magnitude, this means like 0.2 or 0.7 magnitude. So that immediately tells you that you need a very high accuracy in your photometry to measure these effects and in the method that you use. And variable stars, like Cepheids and Ara Lyrae stars, allow you to do that, and also the Cloud Giants. You can do a lot more things with this type of survey. You can look at quasars, you can look at Milky Way objects in the line of sight, and you can look at stellar clusters and individual stars and so on. The data are taken, of course, at VISTA, and then they go immediately to Cambridge, where they do the first data reduction. They produce source lists and images on a one epoch basis. So they combine all the poprints of VISTA to fill in the gaps, and that's called a tile, and they create an image for a tile and a catalog. Then the data go to Edinburgh, where the images are stacked because we obtain multi-epochs on the same tile, and then you can create deeper images and deeper catalogs. Of course, the VMC team has access at the various stages of this process for quality control and also various type of analysis. And in Italy, in Padova, we work on the Poisson function photometry, which allows us to go a little bit deeper in the crowded fields and also around stellar clusters. And also we do the star formation history analysis there. And in Bologna and Naples, we work on the variable stars, Cepheids and Ara Lyrae, and we produce light curves that then become available also to the community. The data access for the community is either via ESO or via the VISTA Science Archive in Edinburgh. This way. These are some of the images of VISTA. Because it's a deep survey, I want to stress this because some people think this is just a stellar survey of the clouds, like many other, but this is extremely deep as some extragalactic surveys for people that look for high redshift galaxies. So we have actually quite a number of extragalactic and distant objects in there, like galaxy clusters and quasars. And if you don't know what to do, you're allowed to do that even during my talk. You can go to the website and look at the images, and you can zoom in and out, and that's very nice. The completion of the survey is going quite well, and you see this in this plot here. This is an extrapolation. 2018 is at the end, and then if you go, these dots are basically the aiming points, and then so we are doing quite well to complete in time. And here about the quality, I spent just a minute. This is the full width at maximum for the K, J, and Y band. And you see that there are two peaks. This is not bad, that's intentional, because in the outer fields, where there are not so many stars, it's not so crowded, we have relaxed observing constraint. And so we allow for seeing in Y of 1.2, and in K also above 1. I remind you that the clouds are at about minus 70, even minus 75 in declination, so you are always at low air masses. So to get this level of seeing at an air mass of 1.6 is quite a very good result. And then here we have the sensitivity for the one epoch, 1 hour, that's how we say, for individual tiles in VMC. So we go much deeper when we combine, of course, all the epochs. This is the status of completion for the bridge and the stream area. So there is a bridge that connects the two galaxies. Everything in blue is finished, and you see that we are almost there. It's 80%, and there are two fields that we placed in the possible location of the stream to look for stellar counterparts, and these are also completed. For the large cloud, the completion goes a bit slower because it's much larger, and also because we are competing in time with the other public surveys, which have targets at the similar right ascensions. And for the small cloud, the situation is a bit better. That's also 80% complete. And there are two fields here that are publicly available, and there are 5 fields here that are publicly available in the LMC. And I'd like to point out that this is the region of Torri Dorados, and this one is the region of the South Ecliptic Pole that we heard. It's an important field for calibration for Gaia, Euclid, and all the missions that go at L2 orbit. So that is the field, and each of these square is about 1.65 square degrees. Compared to other surveys of the clouds, it's very useful. You will hear later about STEP, which is a survey at the VST, There is also OGA4 that is covering a very wide area around the clouds. This is the bridge, SMC and LMC. And then there is a survey which is called SMASH that's complementary to DES. You have seen the DES footprint this morning quite a lot. And SMASH are all these red fields here that are not connected, but they sample quite a large area with a filling factor of about 20%. And these data go really as deep as the VMC, but in the optical. So all of these surveys in this slide are in the optical band. So the uniqueness of VMC is really to push the stellar population detections in the K and in the near infrared. And then, of course, there is Gaia, which is going to survey all sky and provide very useful data for the clouds as well. We have several publications about VMC, and you can look in them up in the AstroPH or in the literature. And they cover a different range of topics, as I said, from Milky Way to quasar to various type of stellar populations, and this number is growing. And perhaps at this stage is a good moment to tell you that because this is a public survey, if you want to get involved with the team and work with the data, I stress work with the data before they become public, then get in contact with me, and this is certainly possible, especially if you have an idea that we haven't thought about before. That's always extremely useful. So let's have a look at the latest science highlights. There is a paper that probably will go on AstroPH very soon. We just sent the revised version to the referee, and that's on the star formation history of the Small Magellanic Cloud. What you see here is a density map for the tiles that were available at the time, somewhere at some point last year, and with a completion rate of 80 to 100%. And what we do here, we look at the star formation in subregions of the size of 1/12 of a tile. Here, one tile is divided in these 12 subregions, which is a region large enough to be sensitive to star formation history and to derive it quite accurately. So if you take bigger regions, you lose accuracy. If you take smaller regions, you lose statistics. And then we do our analysis, and we have beautiful color magnitude diagrams that you can already see without looking in too much detail that change in shape, and basically they are traced in different stellar populations in different parts of the galaxy. And we model these color magnitude diagrams to recover the information that they encoded about the age, the metallicity, and of the galaxy. Also the extinction and the distance, because these are quite important quantities if you aim for high accuracies. So for example, this is only one of these 12 subregions, and you see here a diagram of distance modulo and absorption in the V band. So that's also extinction versus distance. And so we try different type of models, and we recover the best combination. And in this particular field, you will be somewhere here for your extinction and distance modulus, which means we can create maps of distances and maps of extinction. On the right, you have the classical quantities for the star formation history that you want to derive, so the star formation rate, number of solar masses per year as a function of time, and the age metallicity relation. And so we do that for every subregion in all our area, and then we obtain maps of star formation rate, in this case. And you can see, so this is from young ages all the way to very old, 10 giga-year or older ages. And then you can see in detail how the star formation has progressed. So for example, you can see the star formation progressed from the sort of like southwest to the northeast and wing region, where that was more active. There was more active star formation recently. And then you can identify where the burst of star formations were. So these, I can tell you, if you're not on the field, that these are the most detailed star formation history maps of the SMC available today, and also the least sensitive to extinction, because this is done in the near infrared. We find some common features compared to previous studies, of course, that's good. Although it's difficult to make a comparison, because even the most detailed studies that were obtained before were done with HST that covers a very tiny area. So if you move in different parts of the galaxy, you're going to recover different things, different peaks of star formation. So we saw that the star formation was modest at old ages. There was a peak at 5 giga-year and another major peak at 1.5 roughly sorry, this, 1.5 giga-years, sorry. That's wrong units. There should be giga-years. Which corresponds to the interaction probably between the SMC and the LMC. We also look, of course, at variable stars, and I told you that variable stars are extremely powerful to derive the depth of the galaxy. I don't have time to go into detail, but you have to believe me that when you see very tight period-luminosity relation, like in this case, this is period, and this is the Wassernacht relation that involves the K band and the V minus K color, so that makes this relation extinction-free. So this very tight relation with an RMS of the order of 0.07 magnitude allow you to trace the depth of the galaxy when you expect, 0.2 for the LMC and something larger for the SMC. And here you have the light curve of a Cepheid. I mean, Cepheids are fairly bright, so you have a very accurate light curve. But even when you move down to Lyra stars that are much fainter, here you are at a K band of 18, roughly, or even fainter, you still have very nice light curves with very small error bars. The period-luminosity relation is a bit thicker, but this is because there are other effects that play a role here, including metallicity. So we are really working on to this because this is very useful to find out about the structural properties of the galaxies. Then I still have some time, I think. I would like to show you something about pushing the VISTA to its astrometry limits, that's how I say it. So with the clouds, we are at 50-60 kiloparsec. And in this particular region, this is the 47 TAC Milky Way globular clusters, which is conveniently located in the outer parts of the Small Magellanic Cloud. So in this image here, you have the density that is dominated by the star cluster. Here you see an increase in density towards the Small Magellanic Cloud, and then of course you also have the Milky Way and the field population. There is also another cluster here of the SMC. So you have a very beautiful and very complicated color magnitude diagram because you have the overlap of different populations. If you look at these diagrams, these are color magnitude diagrams, J minus K versus K. For the inner region, sort of like between 10 and 20 arc minutes, this is between 20 and 40 arc minutes, and this is further than 40 arc minutes from the center of the 47 TAC cluster. So here you see a population that is dominated by the cluster, the main sequence, the giants, and you have these very faint structures below that don't belong to the cluster, and you have this blue group of objects which are background galaxies. There are lots of background galaxies which are very useful for proper motions. Then you have a region where the populations are fairly mixed, and basically this branch here, the one in the middle, belongs to the Small Magellanic Cloud. This is the red giant branch. There is the clump, which it's right on top of the main sequence of 47 TAC. And then this more vertical branch are the Milky Way giants, dwarfs of and dwarfs, sorry. So if you go further, now you're dominated by SMC population, and there you can see the red clump of the SMC, the red giant branch, that's very extended, and again this vertical sequence due to Milky Way stars. So in this type of color magnitude diagram with this very accurate photometry, you can separate these populations. And in this diagram here, this is the NGC 1-to-1 cluster of the SMC. There is also here the star density. You see that, of course, because the cluster is very crowded at the center, we cannot go very close to it. But when you are beyond sort of like 10 arc minutes, then you find your populations very nicely. And there are lots of objects there. So one of the ideas here is to look at the proper motions. So first you have to split your population conveniently in boxes or in various regions that are dominated by the cluster, regions that are dominated by the SMC, and again this vertical region where you have Milky Way. And then you look at the displacements of the position of each individual star across all your multi-epoch observations. And in this particular case, sorry, I was afraid you wouldn't see the blue points. So in this particular case, the time coverage is 1 year. So it's not really ideal for proper motion when people look for several years, but already in 1 year, we see differences between the proper motion of different types of populations, which is really nice because we are at these distances. So what you see here is the proper motion for each of the, let's see if I go in the right direction here. No? This one. For each of the boxes in this diagram for the three different regions. And the color are as follows. So the light blue are the boxes for the populations that are for the regions over 40 arc minutes, so where you have mostly SMC. In pink, you have the points for the 47 TAC populations mostly, and in black, the one for the mixed region. So, okay. So what you see here is the distinction between the proper motion of populations, which are different populations, right, for the Small Magellanic Cloud. For the Small Magellanic Cloud, we define different boxes where we have giants, we have younger stars, we have red clump stars. So these are all different populations, and they give you a proper motion which is somewhere here. And then you have a region where you have the proper motion of 47 TAC. Again, there is a difference between main sequence of 47 TAC, giants of 47 TAC, because we split them in that way. And then you have regions where you have the expected signature of the Milky Way. And these things are very well distinct for 1 year of data and multi-epochs. For each star, we have something like 96 points to do your proper motion, because there is a point for each detector and taking into account the overlap. So we have 96, sorry, it's not for each star, but it's for each population, so it's 96 independent measurements. If you want to know the details, I'll tell you later. And each of these points contains more than 1,000 sources. So that's why also you have these tiny error bars. And the strength here is also the reference system, because to do proper motion so accurate, you need a very stable reference system. And you can do it with a quasar or with a few quasars, but here we are using a few hundred galaxies per detector. So that's also quite powerful. So now we'll go the other way. Okay, so that's my last slide. And so the point I want you to remember is that there is this great survey. You can go to the website, have a look at the data, have a look at the images. If you're interested to work with the data, let me know. It's about 61% complete, and it's going to finish in 2018. There are public data available that you can use, of course. And this survey is a deep survey in the region towards the Magellanic System, which means you can do many different things with data this deep. You can, of course, investigate, this is our main goal of the BMC team, different stellar populations, distribution of age, metallicity, reddening distance, and to gain insights about this system that is so nearby to us, and that there is still a lot to know about it. And of course, when new spectroscopic facilities come online, we have lots of targets to follow up in this particular region, where we would like to add, of course, the kinematics information and chemistry information. Thank you.
Thank you very much. Thank you, Margarota, also to keep in the time. Other questions?
Going back to the Small Magellanic Cloud, the SMC. So I understand it's not, you wouldn't call it a star version of the others, correct?
No.
So why? Do you know why?
Well,
what's the difference between the SMC and say 15081? 18.
I think it depends how much, well, it's certainly galaxies that had different bursts of star formation, and I think it depends how dominant was your burst to form the galaxy. I'm not really familiar with the specific definition of starburst galaxy, but here we can trace different bursts of star formation. I mean, I can tell you that most of the mass was in place at early ages, before this, I actually have the plot by mass, before 5 gigayears, and the bursts that occurred later on, although they look prominent in this type of plot, in terms of mass, they are not so prominent. I mean, there are certainly recent, and there were bursts at this 1.5 gigayear, and also what is it, 100 mega years ago or so. But in terms of mass, they are minor compared to the assembly of most of the mass of this galaxy that occurred at earlier times.
Well, we know that star-burst galaxies are characterized by two things, and it seems to me that the SMC that we have studied doesn't have any of these two properties. One is the high concentration of gas in the center, and the other one is the high speed of rotation, the differential rotation in the central part of it. These two properties characterize star-burst galaxies, and it doesn't seem to me that you have these conditions.
Well, in terms of gas, the SMC has lots of gas still in the center. That's actually, there is an issue here about what you can derive from the gas and what you can derive from the stars. There is a problem in the SMC because there is still lots of gas in this galaxy, and it's all in the central sort of bar-like elongated region. So that, I mean, I don't have the figure here, but I have it in my computer if you want to see it later.
Audrey.
I wanted to know whether you had looked at the star cluster mass function from the data.
We have looked for the star cluster in the clouds. We are looking into that now. We have I didn't put it in my presentation, of course, but we have actually a paper that is almost completed on star cluster in this SMC in the eastern part and in the bridge, and there we are looking at cluster frequency. And we find some differences compared to the field star formation in that particular region. So we are looking into this. I mean, this particular, I mean, here the peak at this 1.5 giga a year coincides with the peak in the cluster formation that we know. That's why we think this peak is associated to some sort of interaction, but also because we find a similar peak of star formation in the large cloud as well, this 1.52 giga a year. But in the outer parts, and especially in the bridge, there are some differences between cluster and fields.
Great. Thanks to Maria Rosa again. Our next speaker is Matt Jarvis, who's going to talk about the video survey.
I'm going to reboot again.
Okay, so thank you for inviting me to give you an overview of the video survey, one of the Vista public surveys that both Magda and Jim spoke about earlier. So video is the second tier of all the Vista surveys, second deepest tier behind Ultra Vista, and for that reason it has certain niche science you can do with it that you can't do with Ultra Vista and you can't do with the next tier down, Viking. So just like to thank a few people, Boris Heusler, who's basically the postdoc working on this and doing a lot of work for it. Also a long list of people at the bottom who have done various pieces of work and helped tidy the data up and do some quality control along the way. As Magda and Jim both said earlier, the video data is public. The latest updates you can actually get from the video webpage in Oxford, although it's the public data released through both ESO and the Wide Field Astronomy Unit at Edinburgh. I should also give special mention to both Wide Field Astronomy Unit at Edinburgh and CASU, who basically, CASU do the initial reduction of the video data, we do the stacking and the source extraction and generate catalogues, and then the Wide Field Astronomy Unit actually do a lot of the I'd say grunt work in delivering this to ESO. Okay, so why move to the near infrared and why is Vista important? Well, in terms of extragalactic astronomy, this is the usual view of what you get at optical wavelengths, and this is the red shaded region in a typical SED of an elliptical galaxy. And as you move to high redshift, all that red light moves out of your optical window, and therefore your ability to measure the total stellar mass in galaxies becomes very, very difficult because all the stellar mass is actually contained within that red population. Whereas things like star-forming galaxies dominate your optical window at high redshift. The mass-to-light ratio of those blue stars is basically more light than there is mass there, so it doesn't give you an accurate representation of the bulk of the stellar mass in these galaxies. So obviously, as you move to the near-infrared wavelengths, all that elliptical galaxy light or old stellar population light remains in your near-infrared band, and these are the VISTA filters, ZYJHK. You see, you retain the bulk of the longwood of the 4,000 angstrom break, where the bulk of the stellar mass is, all the way out to redshift 3 and 4 in the K band. So that's the main redshift range we're looking at with video, is the redshift range between redshift 1 and 4, where we have a representative volume of the universe to understand galaxy evolution as a function of things like stellar mass, environment, the evolution of galaxy clusters, and AGN, etc. So you've seen this plot before, so I'm going to skip over it. So the main goals, like I said, galaxy formation over the epoch of activity. So we're actually sensitive enough to detect a typical L-star galaxy out to redshift 4. And it covers 12 square degrees on the sky, so that gives you enough volume in the universe to actually pick out the like high redshift massive clusters, tens of 10 to the 14 stellar mass galaxy clusters above redshift 1. It's actually deep enough to detect massive galaxies all the way into the epoch of reionization, and I'll talk about that a bit more later. And this redshift range of 1 to 4 is actually critical if we want to understand the role of AGN-driven feedback in the universe. Because this is where the peak of accretion activity and the star formation activity occur. And also, the video survey has actually got a link to the dark energy survey, which you heard about this morning, and the deep supernova cosmology fields for the dark energy survey are actually over the video field, so we also have optical data from DES. So it's been allocated around 200 nights, and it began operations about 5 years ago, and expected to be complete in the next couple of years. So it's covering 3 different fields. The 3 famous extragalactic fields with a wealth of ancillary data. Notice this doesn't include Cosmos, because Cosmos is basically the Ultra Vista part of the Vista surveys. And this is covering the what are originally the sort of ISO field, so extragalactic fields, also the Herschel fields, the Spitzer-Swire fields, and a range of other data in here. And these red boxes here are the Vista tiles, each about 1.5 square degrees in size. And in 2 of the fields, Ekman LSS and Chandradeep Field South, we have 4.5 square degrees, and we have 3 square degrees in LASES 1. Now, when we started, the original survey was defined as this, with these depths in AV magnitude. As the survey went on and we realized DES was actually going to be more efficient at Z-band, we actually reallocated a lot of our Z-band, the remaining Z-band observations, time allocated to that Z-band, and put it all into the Y-band. And that's very advantageous for picking out very high redshift galaxies. So the depth of the Y-band data will now go down to about 25.6, with commensurate depth in JH and KS. Okay, so this is a pretty image from the video survey, and to put it into perspective, this is only 1/100th of the total area of the video survey, and this is just near-infrared data. There's no optical data being used in this. This is actually YJK composite. And that's the size of the moon. And one thing I like to show when people are studying high redshift galaxies is that's the size of the Hubble Ultra Deep Field. I mean, this is only 1/100th of the total video data. It really shows the kind of power, the kind of science you can do with this. Okay. So, in terms of volume surveyed, like I said, video is the next tier down from Ultra Vista. And for that reason, it allows you to access a lot more cosmological volume to high redshift. It's about a factor of 10 greater in volume than you can observe with Ultra Vista or Cosmos. But for those of you who work on Sloan, if you take Sloan out to redshift 0.2, let's say, it's a similar volume at high redshift that Sloan gets at low redshift. So that's great. It allows you to do all this work as a function of environment, study galaxy evolution as a function of environment. Okay, so we heard a bit about photometric ratios yesterday. Just want to point out that the addition of these, whether 4 or 5 near-infrared bands, actually helps your photometric redshift enormously. Unfortunately, I can't actually show how much it improves things because all the spectroscopic data we have to compare against is all at lower redshift, and therefore the power of the near-infrared data is actually gives you power at higher redshift where that characteristic 4,000 angstrom break is redshifted into the near-infrared. But spectroscopic redshifts are scarce in that region, so I can't actually plot spectroscopic redshift against photometric redshift all the way out to redshift 2 here because we don't have enough spectroscopic data. But even out to redshift 1, the near-infrared data really improves on things compared to just a purely optical survey. This is data from the CFHT Deep Legacy Survey. And you basically improve your accuracy of your photometric redshift by about 30 to 40% by including the near-infrared data, and that's up to redshift 1. But you can actually do neat things about removing the sorts of objects that hinder your photometric redshift. So in this case, if you actually pull out everything that has colours consistent with an AGN essentially, then you can actually reduce your outlier rate substantially. Okay, so the core science of video is galaxy evolution. So I'm just going to present some various parts of the work that's already been done or we're doing on video. This is a plot of the stellar mass as a function of redshift. For 1 square degree of the video survey, where we have very good optical data already from the CFHT. And if you fold in all your uncertainties about SED fitting and photometric redshift fitting, this is your mass completeness depending on the range of your mass completeness depending on your template that you're using for your galaxies. So this tells you can't just pick your best fit photometric redshift and best fit stellar model and define a mass limited sample like that because you have all this mess depending on what kind of template you're using. But if you do this properly, which Russell Johnston has been working on this for the past 6 months or so, then you can pull out the evolution of the specific star formation rate as a function of stellar mass and compare things like the latest hydrodynamical models. And you can see that what I want to really emphasize is the combination of area and depth of video allows you to go from relatively L-star kind of massive galaxies out to redshift 1-ish, all the way up to the most massive galaxies, all the way out to redshift 3 and 4. And this is a plot of star formation rate against the stellar mass, compare the grey shaded region and this solid line turning to dashed line here is the actual data we have from video, the derived constants from the data. And this is a comparison with various models, either semi-analytic or hydrodynamical from Illustris and Horizon and so on. And what you see is none of the models really agree with the data, which is nice from an observational perspective. It means there's still a lot to do, but there's also a lot more to do for the simulations kind of people as well. So the vast majority of the simulations actually underpredict the amount of star formation to give the stellar mass compared to what we observe. I said earlier that the depth is good enough to get to the very highest redshift, all the way out to redshift 6. And this is some initial work from Chris Willett, published last year, on actually constraining the bright end of the galaxy mass, or the galaxy luminosity function at redshift 6. I'm not going to dwell on this, but it's usually using the usual sort of alignment break galaxy kind of selection, and feeding in, this is actually a combination of work using both UCAS UDS and CFHT WordCam data as well as the video data. And I think Jim showed this plot earlier from Rebecca Bowler, who's basically improved on this work using a combination of video, UCAS UDS, and Ultravista and Cosmos. The reason why video is very important in this is when the UCAS UDS does not have the wideband, and therefore the video wideband is actually giving the power here to actually do this work over the UCAS UDS field. And again, although I'm not showing it on this plot, the models generally don't go through the data, but the key point here is these black crosses at the end are actually the only constraints you can get on this bright end of the luminosity function of redshift 6 is from these ground-based, relatively wide area data that goes deep enough to pick out these massive galaxies. The other aspect, as I mentioned, is looking at the environment and things like halo occupation distribution modeling to work out how the baryons basically trace the underlying dark matter distribution as a function of redshift. There's some preliminary work from one of my students, Peter Hatfield, looking at the correlation between low mass, say, satellite star-forming galaxies or satellite non-star forming galaxies around more massive, what you might imagine to be central dominant galaxies in dark matter halos, and looking at how that relation may change over cosmic history. You can see the characteristics of halo occupation distribution shape here, where you move from the single halo term to the two halo term in the angular correlation function. Again, you can look at things like the environments of AGN and look at what triggers AGN activity. And again, the wealth of data over these fields helps you in this. In fact, you can select things at AGN at X-ray wavelengths or at mid-infrared wavelengths or at radio wavelengths. This work that Marios Carouzos did on actually looking at the close environments of AGN activity as a function of redshift. And not only can we select the AGN, but we can also select the control non-active galaxies to actually allow a fair comparison split in terms of mass and environment and so on and so forth, and actually see if there are any differences between the AGN and a normal massive galaxy at these high redshifts. I noticed there's a poster at the back doing a similar kind of work on the Cosmos field, so this is where we want to go if we want to understand AGN-triggered feedback at high redshift. We need to understand the merger history, if mergers actually do cause the AGN activity that then causes the feedback or not, or is it more secular processes? Some work by another one of my students, Sarah White, who's been looking at the star formation activity in a very well-defined quasar sample using the wealth of optical and near-infrared data here. Select the cleanest quasar sample we possibly can, and the near-infrared colours really help here to actually remove a lot of the contaminants. And what we have here is actually combining it with radio data to actually understand how much of the radio emission in radio-quiet quasar is either coming from the host galaxy due to star formation or due to the AGN accretion activity. There's been a lot of work in the literature recently purporting that this is due to the star formation in the host galaxy, whereas if you actually calculate the star formation rate derived from the radio luminosity and the star formation rate derived from what you expect if they lie on that sort of stellar mass star formation rate main sequence, then you have way too much radio emission for it to be explained by star formation, which indicates, at least in quasars, a lot of the radio emission is actually coming from the accretion activity rather than star formation activity in the host. So I've mentioned the wealth of ancillary data. So some of this is in place, some of it is still being gathered, and some of it is in the future. So I haven't mentioned that a number of years ago now, we also got allocated 1,400 hours of Spitzer warm mission time to cover both the video survey areas and two fields in the north that have UV coverage. And this provides 3.6 and 4.5 micron data to a similar depth of what we get to with the K-band in video, giving us that longer wavelength anchor to actually be able to measure things like stellar mass to actually higher redshifts than we can do with video alone, and also improves on the photometric redshifts. There is guaranteed time VST observations that are also in these fields doing supernova cosmology work, and as I mentioned, DES is also covering these fields. It's already covered by Hermes, and it's also going to be covered by, this should be AXPOL, not ATCPOL, deep fields to do CMB SZ work, as well as lensing of the CMB in cross correlations with high redshift galaxy populations, and so on and so forth. I was saying to a few people yesterday, actually my hat for this conference is VISTA and deep near infrared data. My other hat at other conferences is SKA related, and MeerKAT related and ASCAT related, so all the future radio surveys. And to point out that these fields are being covered with the MeerKAT South African SKA precursor telescope, both in an H1 deep survey over the Transit Deep Field South, and also with a radio continuum survey that will be roughly around a factor of 10 deeper than anything we have at the moment over the full video survey area. And then, to put it into context, this allows you to get Milky Way type galaxies out to redshift 3 in the radio continuum. So, I'm also going to mention, sort of a precursor to Mathias' talk on Friday, that all this data and other data is actually trying to be brought together under an EU-funded project called HELP, the Herschel Extragalactic Legacy Project, to actually provide a database of not just the data and the catalogs, but value-added data like photometric redshifts and their probability distribution functions, star formation rates and their associated probabilities, and stellar masses, all these things I've talked about, into one sort of super database where people can actually access all this, and you don't have to get your hands dirty with things like Herschel data and Spitzer data and radio data. You can actually just go and actually pick out the quantities you want from this. I'm mercilessly going to advertise that there's a 2-year postdoctoral position in Cape Town if anyone's interested in working on this project. So what is happening with video now? So video science is mainly done over, at the moment it's only been done, well, it's been done over many square degrees, but the first data release is only one deep tile, which was coincided with the CFHT LSD1 field, which had exceptional optical data, which allowed it to do a lot of the science I presented. But we've just sent off it's actually the third data release, but it's the second data release of the deep data, and that actually covers around a 3 square degree contiguous coverage in the XMMLSS field, down to the full depth in all 4 or 5 filters. And there's actually some data in the third field as well. In LASS1, there's 3 square degrees coverage in all the filters apart from the J-band. Again, that's with ESO waiting for approval, so that'll be out to the public soon. You may have noticed when I showed where these fields lie on the sky that they're separated by about 3 hours in right ascension, which is not ideal if you want to conduct a survey over these fields, and they're all basically fighting for each other for time on the telescope. So actually the Chandra Deep Field South is actually lagging behind because it was essentially competing for the same bit of sky time as XMMLSS, which it chose to prioritise for various reasons. So over the coming year, Chandra Deep Field South will catch up because XMMLSS is more or less complete, and we should be well on the way to having the full video survey data. And this is basically saying the same in a tabulated form, and to give you an idea, so these are 70 hours have already gone into the Y-band on all of these 6 fields, and Chandra Deep Field South is lagging behind. And the K-band coverage is actually more or less complete now in all fields. Okay, so just to summarise, video is being used for a wealth of different science, and now that we're moving from sort of competing with the Cosmos Ultra Vista kind of scale of one single pointing, which we have been for the past three or 4 years, we're actually moving into the realm which video is designed for, to actually provide this much wider area deep survey. And for that reason, it's not a surprise to me that over the past 2 or 3 months, a number of groups have emailed me saying, can we get our hands on this data? So if you want to get your hands on this data, all you have to do is email me, and I basically send you a password and a link to the way you download the data for, you can get on with it. Unless you want to wait for it to be ingested into ESO and WIFAO, which you can do, but you can actually just download the DeepStack data at least quite easily from our webpage. So all this range of science, there's been about 17 refereed publications so far that I know of, some of which doesn't involve the video team, but most of which does at the moment. Like I said, you can download the DeepStack from this page. If you want to do variability kind of science, things like picking out high redshift supernova or doing AGN variability studies or anything else that goes bang in the night, you can actually download the individual paw prints and the source list associated with those paw prints from both ESO and the Wide Field Astronomy Unit in Edinburgh. Should mention, so a paw print is actually about 20 minutes of data compared to the sort of tens of hours that we're spending. So there's a lot of paw prints that go into making these DeepStack images. So there's a lot of actually cadence there you can actually look at and look for variability. Mentioned earlier that this is all going to be ingested within this HELP consortium, and again, if you want to know more about this, talk to myself or Mattia Vicari. We're happy to help with any of that. Okay, thank you.
Thank you, Matt. Before I ask,
Think about some questions, but the Massimo and myself would like to know what paw prints are.
Sorry. So if you remember both, I think Jim and Maria Rosa's talk, the VISTA focal plane is actually made up of 16 detectors, and there are gaps between them.
Right.
To fill those, you have to do 6 jitters on the sky. But a paw print is just that, those 16 detectors that haven't been moved around to fill the whole of the focal plane. Okay.
Thank you.
It's like a paw print.
Yeah, paw print. Other questions? Stefano?
We would like just to know if there is any news about Irish cluster found in.
I was going to actually, you tell me. We haven't actually, so Jim Geach was working on this, but and he has a draft paper, but it's not finalised yet. There are potential high redshift clusters, but we've only really looked at the 1 square degree with the CFHT coverage at the moment. When we start combining it with dark energy survey data, I think will be more the time to actually pick out at least the most massive high redshift clusters. There are signs of groups, well, it depends what you class as a group and what you class as a cluster, but there are signs of at least over-densities of galaxies up to redshift 2.
Matt, I have a question on your first plot, when you plotted the star formation rate per stellar mass as a function of redshift. Now the other one split it by stellar mass.
Okay, that one.
That's right. So if I read correctly, at the highest mass beams, the green points in the bottom panel, down there, so that you have no data below redshift 1.5. Is this the downsizing we are seeing? Which I would agree.
No, it's just a lack of statistics in 1 square degree for the most massive galaxies.
Oh,
you can
yeah.
actually see it up here, that 10 to the 11 here, well, there's this massive drop off here because of the flux, the area coverage of the survey.
Right.
This is only 1 square degree though.
Okay, so you're going to catch them at some
We
point.
will get them with the full survey.
Fantastic.
We go a factor of 10 wider than this. So.
Simon?
So Matt, infrared backgrounds are a nightmare, I guess, to work with. So do you think you've got control of your backgrounds? I mean, are you doing background subtraction for each individual paw print and then combine them? How do you guys do it?
Yeah, so it's sort of an iterative process when you go to the deep fields. What we do is we actually do the combined deep field data with a very nominal sky subtraction, just taking a median kind of sky. And then we create a mask of all the objects. And we use that mask to create another sky flat, essentially, and propagate that through and do the whole business again. And then we actually do that as many times as we need to. So it's sort of an iterative process because you need to mask out all your galaxies before you make your sky frame because they're all contributing to your sky at some level. So yeah, it's a lot more difficult. In the K-band we take an image every 10 seconds. And well, we take an exposure every 10 seconds, but we take a stacked, well, what we call, it's sort of a 60-second exposure is what we really have in the end. So we're imaging every 60 seconds. And the sky background does vary on that timescale, mainly the K-band, but we're pretty confident we can deal with it. It's actually looking quite good. It's actually, I mean, if you look at the actual data quality of both UltraVista and video, I was amazed how good the data quality was compared to what we've experienced with UKIDS, where there are a lot of teething issues with UKIDS. We haven't really had those problems with the VISTA data.
Time for another quick question, which if you don't have, I ask. The star formation rate, are you using far infrared or are you getting it through the ACD50?
So what we're doing is using SIGAL and doing the full energy balance between the UV to the far infrared, where we have far infrared detections. We have actually tested what we get if we don't use the Herschel data and just go up to 24 microns. And they are consistent. You just add more scatter on your star formation rate derivations if you don't have the Herschel data. But it's all pretty consistent. So we're trying to do it in a full probabilistic manner using all the data we have.
Thank you. Thank you very much, Matt, again. The next speaker is Georg Melnick, who is going to tell us about the ESA commitments in mapping the star.
There we go. Okay. Okay, thank you very much. I'm really pleased and honored to be here to celebrate Massimo's birthday. He's been a legend in astronomy ever since I know him. It's a long time. Last time I came to Naples was actually to negotiate with Massimo. We were doing some business. I have to be very honest with you. I don't remember the details. It had to do with the wide field imager that was being put together for La Silla, and we had to have these discussions. And probably I forgot to tell him that I was coming, because when I arrived, he was fully busy running for candidate for the municipal council. So I said to him, and so he said to me, sorry, I don't have time to discuss with you, but let's come with me to the various election activities that he had to do. It was a very busy schedule, so I accompanied him all over the town. It was very nice. And so at the end I said, okay, we'll do the following, Massimo. You'll get an hour of serving time for every vote that you get. I don't remember how much time you got. But it was very nice. I had the greatest recollection. That was more than 15 years ago. It's a long time ago. So I am, I've been asked, this is the title I've been given, to review the ESO commitment to mapping the southern sky. And here's an outline of the talk. Putting together this talk, I realized that throughout my whole career at ESO, which started in 1977 in Geneva, I've been involved with mapping the sky. I didn't realize that before this talk, so thank you again, Massimo, for illuminating me. So I'll just say a few historical remarks. I'll talk about the imaging surveys that were not mentioned here so far. They'll be very short. I'll say something about the spectroscopic surveys, then future. And then if there is time, I'd like to make a couple of points that are relevant to what we've been discussing here from my own experience of using these surveys for my own science. So let me begin. So here's a historical picture. You'll notice that the NTT is missing. This is a really old picture. And the Schmidt telescope is right there. And that was our first commitment to mapping the sky. It lasted for a long time. And I'd like to tell you about the 3 lives of the Schmidt that you may not know. The first life was actually the survey itself. And there was the ESO ECRC survey, and ESO was taking the red plates. And there was this famous Quick B. I don't know if you remember the ESO Quick B survey. And here are some legendary figures of La Silla. There were the 2 Pizarro brothers who were the operators of the Schmidt telescope, and Hans Emil Schuster and his beloved dog Sonia. And you know, this was ESO's first endeavor for plates. And I actually was involved in this, not in taking the plates, but when I arrived at ESO in 77, I became sort of responsible for the machines that we used to scan these plates. We had an optronics machine and a PDS, and that was my involvement. Now the second life, here it is. Around 1995, we decommissioned the telescope, and then we needed a place to store the wine. That it has to be fresh, and all of the things that wine has to be. Now wine was an important part of the history of La Silla, because when I assumed as director of La Silla in '94, I arrived. That was when Ricardo Giacconi came as director general, and this was the time of intense conflict between ESO and the staff. When Ricardo first visited Chile to go see La Silla, he was welcomed by a full-page announcement in El Mercurio saying ESO violates human rights. So that was the beginning of a very difficult relationship. So having parties and social activities became an important part of trying to mend this schism. And so we had to store several thousand bottles of wine somewhere. And that's what La Silla. And as you see, The cheap wine was on the floor, but the good wine was stored here in the focal plane, where all good wines must be. Now the third life has just begun, it's the famous La Silla Quest. So now we go into the surveys. This is a variability survey, which is being conducted by a consortium of Yale and Indiana. They started in 2009. Here are the details of the technical details. They're using one single broadband filter, although they have more filters that they can use. They survey about 1,000 degrees per night with different cadences, and you see with different colors here with different cadences. They found about 400 to 900 transients every night. Here's the camera. It's an impressive camera with 9.6 square degrees field of view. And they installed a direct link to Cerro Tololo. It's a direct radio link, high, you see by the size of the antenna, which is a high throughput link. And so they, in real time, they radio the data to Tololo, and at Tololo they have a high-speed fiber to the US. And so the data goes every night in real time and gets processed because you have to do that. The cadence of the service is such that unless you process the data every night, you don't. You might as well throw it away. So that was the third life of the Schmidt, and it's interesting, the Schmidt is still going and still serving the sky. Another historical piece was this famous Dennis survey. Probably nobody remembers anything about Dennis. Dennis was not a very successful survey in the end because TUMAS came along at the same time, and TUMAS was doing so much better in the K-band than Dennis that TUMAS superseded that. But still they did the I-band, which TUMAS wasn't doing, and at the end they had a 91% completion of that survey. This was the La Silla 1 meter telescope, which was dedicated to that survey for 7 years. And this was a consortium of institutions from France, the Netherlands, and Vienna. Then there was a famous ICE survey. I don't know if anybody remembers ICE. We had this saying that ICE is nice, but at twice the price. And this was an invention of Alvio Benzini and Luis da Costa, who said, look, we're going to be commissioning all these 8-meter telescopes, so when are we going to point at them? We need surveys. Now we see now from this, what is happening is that we have all the surveys, and then we say, well, how are we going to follow up the surveys? Oh, we need more surveys. So we go from imaging surveys to spectroscopic surveys, and, that's how it goes. So ICE was a mess. And the reason ICE was a mess is that it used so many different instruments, which, different telescopes, different instruments. The pipelines have to deal with all kinds of peculiarities and idiosyncrasies of instrumentations, and they have to be continuously adjusted. And here we have the creators, Alvio. I couldn't find a photo of Luis in those days. But in the end, if I looked at the people who worked on the ICE survey, I see many, familiar faces, people who are now leading survey efforts in ISO, in Europe, say. So that's very good, at least as a training ground and as a place where experience was gained. ICE was a nice thing. Now, this guy's also had a second life. As you see, Alvio grew up to become a tourist guide in Venice, and Luis is trying to run the whole of Brazil. So he invented this thing called Linea, and but in the meantime they did goods. They did this famous ISO goods spectroscopic survey. Well, it was also imaging, but the most important thing was the ISACS spectra of goods. So they kept on doing surveys, and Alvio is still involved. If you look at the proposals that we regularly get at ISO for spectroscopic surveys, Alvio is always a co-author. Now let me just say a little thing about these wonderful little telescopes, because we tend to forget them. But they're there, and they're serving, and they're producing enormous amounts of papers and incredible amounts of data. So only 3 of them I'd like to mention. TRAPPIST is a Belgian project, and being Belgian, you know what they're doing. Asterosseismology, right? Well, REM is the Rapid Eye Movement, this telescope which was originally developed to follow up gamma ray bursts. Then gamma ray bursts turn out to be much fainter than expected, so it does everything else. Tarot, same thing. So they are used a lot of the time for other things because they can just not detect the fainter bursts that are produced by satellites nowadays. And then this is the NGST, and I'll say a little bit more about the NGST. There are 12 of these small telescopes which are independently steerable. Each of them has a field of view that I forgot what it is, 3 degrees. So you can look at 12 times 3 degrees at the same time. And this is a transit survey. It's the new generation transit survey that is going to be looking for Neptunes and super Earths. And it's going on Paranal, in this region, on the way to Vista. So if you guys go to Vista, stop and visit these people. They're nice. They are used to transits anyway. So you just go. And so this is another survey that's going on right now at La Silla. Sorry, at the ISO. So let me say a few things about the spectroscopic surveys. This is just a list. I've listed here the ones I could remember, the ones that were mostly public surveys rather than large programs. Let me just say a few things about each of them. Goods, I will not go any further than what I already said. VVDS, the final release of data has already happened. This is from that paper. Here are the details of what they found. They found almost 35,000 galaxies, but about 8,000 of them or more have unreliable redshifts. And one result that I like in particular is this early result by Gigi Guzzo of redshift space distortions, where by doing the two-point correlation function in parallel to the sky and perpendicular to the sky, you can put constraints on the gravitational forces that are creating structure formation. And here is their result, and you see that you can't really tell from different theories of gravity what happens. I mean, the error bars are huge, but nevertheless, it's a promising first step. This is the result from VVDS that I personally like the most. Then after VVDS came Vipers, and Vipers is again to do this redshift space distortions, but with 100,000 galaxies rather than 20,000, 25,000, so that they can reduce the error bars. And this is the specifications of Vipers. There are two fields. They're serving a little bit more than about 23,000 square degrees. Their aim is to reach 100,000 galaxies in this redshift range, and this is their preliminary results. And again, this is redshift space distortions, where there's nothing here that is scientifically new, except that they validated their modeling, the techniques that they're going to be using to reduce the data, which are the red and the blue contours. There's a paper that just came out. Vipers has released about half of the redshifts already, and the other half should come soon. C-Cosmos, well, what can I say? Quenching. It's a word that I don't like. It's this thing that when you plot galaxies in this plane, color versus mass, then they are either red, and they call them the red sequence, or they're blue. Sorry, the other way around. They're either blue in the blue cloud or red in the red sequence, and there's almost nothing in between. And they ask the question, well, how could star formation have stopped so violently? This is what they call quenching. So C-Cosmos is a survey that is looking at this in the cosmos field. 20,000 galaxies have been released, and that's where we are. I think all of these surveys are completed in terms of the observations. The releases are coming. Now the latest of this is Woods. Woods is wood in general. Here are the specifications of the surveys. Again, they are planning to deliver 10,000 galaxies in this redshift range, and they're looking at 3 specific fields. The areas that they're covering are here, about a square degree to that depth. And here are some results from WOODS. Well, the basic result that I want to highlight here is that almost all or most of the high redshift galaxies that are known have been detected in one of these surveys that I mentioned, at the DISO public survey. So our commitment is pretty stark. Okay, now there was a new call for public spectroscopic surveys. Mike already mentioned this, so I'm not going to say more about that, except just to show you some statistics attesting to the large interest of the community to doing these surveys. Now, the committee, this was a very high-level committee that was looking at these surveys. The first time around, they didn't accept any extragalactic survey with VMOS. The last time they passed the FLAMES and the PESTO surveys that we already spoken about, and they said these surveys don't have enough legacy value. You know, people are going to point the telescope to the targets they want, they're going to get the redshifts of the galaxies they want, and what's the legacy value? So they insisted very much that these surveys had to have legacy value, and that led to the selection of these 2. And if you read these proposals, they say at the beginning in the abstract, this is not a redshift survey, in capital letters. So, yeah, and then they go on to say that this is something else. But it's okay. Now let me say something. I think I was asked by the organizers to say something about sub-millimeter surveys, and I will mention these 3 that have been done with. Well, these 2 have been done with APEX. The third one is in progress. ALMA is not doing any surveys right now. It is just doing pointed follow-up observations. As of cycle 4 of ALMA, there will be calls for large programs where people can ask for them time to do some surveys. But now, right now, that option is not available. Okay, now, and for those of you who don't know APEX is a telescope which the Atacama Pathfinder experiment is on the ALMA site. Okay, 5 minutes. You will miss the action. So this is the atlas of the galaxy. This is the acronym starts for that. They're mapping the whole Milky Way within at 1.5 degrees, so a 3-degree wide band over the whole galactic planes visible from Chakrantor. And what they're looking for, this is done with La Boca, the La Boca bolometric camera. They're looking for hot dust or for dust emission at 870 microns. And this is a montage of the La Boca observations, the hot dust on top of the mid-infrared light in the galactic center. So it's such a region. This survey with this fantastic acronym, we're getting better and better, aren't we? Is doing the same as Atlas, but in 12CO, sorry, it's should be written something. It's 13CO and C18O, so these 2 molecules. So these people are producing cubes rather than images. And here is an example. Comes out particularly bad, so I'll skip it. And finally is the LESS survey. It is the La Boca survey of the extended Chandra Deep Field South, and it's a big area for these kinds of detectors. Although La Boca has a superb mapping efficiency, they have found 126 sources, sub-millimeter galaxies. And this is just to remind all of us that in sub-millimeter galaxies, or lyrics, however you want to call them, most of the emission comes out at the far infrared. And so this is going at 870 microns. And so what they get, of course, are the SEDs over a wide wavelength range, and here are the points which are assured by the LES survey. And then these sources have been followed up by ALMA. So this is, but it's not, excuse me, about a public survey. Now let me just conclude by speaking about the survey telescopes. There are two, well, not survey telescopes, but survey high multiplex survey spectrographs. There are two. There's moons, and all of the details of moons are here. They will have 500 object fibers and 500 sky fibers, and this is the wavelength coverage and the resolution. And then foremost, which is going to go on VISTA, moons goes on the VLT, I'll show you later. This is still in this stage where all options are open. And let me just show you an artist's impression of moons. So moons goes on one of the VLT UT telescopes. Here it is, shown there. Here's what the acronym means: multi-object optical near-infrared spectrograph. And I'll have to go very fast through the science, but there is a galactic science case, which is basically extending the Gaia science case all the way down to 20 minus 20 V, so they will be able to see to the far reaches of the galaxy. And then, again, redshift space distortions, and these are the predictions of what one will get with the moon survey. You see, here are the previous Guzzo et al. Error bars, and they will be able to constrain much better. Thank you. Foremost goes on the VISTA telescope. It will replace the camera by a rather complicated fiber positioner system that goes in here where DIRCam is, and there will be the high resolution spectrographs and the low resolution spectrographs. The main extragalactic science case of most is to obtain redshifts for the eROSITA clusters. So they are looking to obtain redshifts for 50,000 eROSITA X-ray selected clusters. And the galactic science case is, again, they will be able to determine the full 3D combined with Gaia, because they will get ray velocities and proper motions, they will be able to get the full 3D potential of the Milky Way. Now, I don't know if I have, let me just tell you what the status of these things. Moons, the contract of moons has been approved by the ESO Council, and they're going ahead. Foremost is supposed to be presented either at the next council meeting or the following one for approval. Foremost is a bit more complex because of the way the public is going to benefit from this survey. Since it's with fibers, the fibers will be pre-allocated and this instrument will be operated by the consortium. So there are a few political problems to clarify, but these projects are going ahead. So let me conclude by just saying that we're mapping. Thank you very much.
Thank you very much for this fantastic, enjoyable talk. Other comments? Daniel?
I thought I was going to get to showing you my stork diagram, which I came here.
Yeah, so thank you very much. I've got a question that came up in discussions yesterday about follow-up. So, because you were talking about commitment and mapping, can you comment on this, how ESO, or whether ESO are discussing how to help the follow-up issue of, all the sources that are being found in mapping the sky, and they need to be followed up, and facilities aren't really available to do that in future. That's something that is being discussed at ESO. Are there thoughts about address this.
You don't think these are enough? I mean, we are.
It depends on how they are being used. If they are surveying, if they are mapping their own sources, they're not following up sources that other surveys.
Well, in the
are.
case of
following up like transient objects or whatever it is, or also from imaging surveys, spectroscopic follow-up is not necessarily possible through those.
In the case of follow-up, we had these two modes, right? Either you say you're going to follow up in some sort of a public survey mode, or you can always ask for a large program that will allocate a large amount of time for a longer term, say 3 years or 5 years, and you can do your particular follow-up. But if you want to follow up everything, then you need to use one of these instruments. You have to wait for Foremost to finish its mission so that you can take a spectrum of everything else. But large programs are still there. And even with moons will not be fully dedicated to.
Yeah, I guess especially in transient mapping, you need a much faster mechanism to follow up. So you probably would need large telescopes that are available on very short timescales. So any proposal.
How large? I mean, there's always the 4 meters. I forgot to mention. I didn't have time to mention this. There is a call for new instruments on the NTT, and we received 19 proposals. Very good proposals. We've a few. I think 6 of them have gone to the next phase in the competition, and at least one of these instruments is exactly aimed at following up transients. But that will be on the NTT. If you want to follow up transients on the VLT, it would be much more difficult. But these transient surveys are using exposures of 1 minute, so they're bright sources.
With all these wonderful imaging surveys taking place, I wonder whether a 4 meter is big enough. I mean, does ESO have plans to build a bigger wide field survey facility? Because MOONS has a small field of view. It's very easy to it's very difficult to modify one of the VLTs. Perhaps what we really want is a 12 meter dedicated wide field survey telescope.
I forgot to tell you. I retired from ESO Novus. So I'm sorry. But during my days as the only heir of Alvio Rancini, this came up and again, and ESO said we don't have the resources to do that. But
Now we conclude, but let me mention that I saw a preliminary result from DUDS by Olivier Lefebvre and his students, and this is spectroscopy of 5,000 redshift 5 galaxies in detail, and I can tell you the results are amazing. Now I'm not going to say now because it's confidential, but they are showing downstairs.
Can I show? Do I have 1 second to show one?
You don't, but
I came prepared to. This is the stuff Okay. I'd like to ask you, how many of you have seen this plot before?
No one.
This is one of these correlations that we call a Stork diagram. Nani, of course, he knows that. Well, what's being plotted here is the consumption of chocolate per capita as a function of Nobel Prizes.
The function of
Nobel Prizes per million inhabitants.
Do we say which chocolate? Because you have sweets.
Chinese don't eat the chocolate. And the reason I brought this up is because when you see these correlations between luminosity and luminosity, which have a slope of 1, and they're fantastic, remember that you have the distance square in both axes. You take the log, you can't get a correlation. So this fundamental, this main sequence. Okay.
Thank you very much, Jörg. The next speaker is an engineer, if I'm not incorrect, who is going to tell us, Engineer Cimino is going to tell us about the Italian industry clustering program.
Thank you very much, and first of all I'd like to thank you very much the organizer for providing us the opportunity to give this presentation today. and talk on our initiative. And I also like very much to express my warmest congratulations to Professor Capaccioli for all the achievements he has made and for all the things that he has allowed us to learn from his many things that he has done. The initiative I will be talking very briefly today is an initiative that we have been working on since some time now, which has been undertaken by a number of companies here in Italy who are trying to materialize the best possible conditions for their involvement as well as for the involvement of other companies within the large programs like the SKA, because we of course believe that these programs are very important also for the companies like ours, for the opportunities they can provide to develop technology which can have a very many number of possible applications besides the scope for which they are designed for the telescope. So we believe that big programs like the SKA will give the opportunity to the industry to develop technologies which from one side will be useful for the telescope construction, and from the other will also be able to provide opportunities for their employment, their use, their utilization in a number of possible applications that will follow. Of course, one side effect of this is also to materialize or to contribute to materialize the opportunities for a most large procurement policy that can eventually lead to some kind of hybrid just return basis, which are important for the overall frame because they can allow to design a larger participation of the country in programs like the SKA. The cluster we have formed is now formed by a number of companies that you can see listed on this chart, and there are 6 of them at the moment which have very large expertise in a number of activities, mainly electronics development as well as communications technologies, and also they are very clever and very competent in activities like design to cost, operations capabilities, maintenance policies, all these things that can provide eventually the possibility to manage the system once it will be in operation in the best possible way. We also have another 3 or 4 companies which are dealing with us, and we are discussing with them way for them to be also part of our cluster. The action we are taking now on these days is mainly based on 3 planes. One is the technology and capability development, because we want to be sure that we are in the right track as related to the needs from the project from one side and the time frame which is involved. The other one is a discussion we are developing with a number of consortia which are already involved in the pre-construction phase of the SKA. We have a few negotiations that are going on, and some of them are quite advanced, and we believe that we will eventually be able to enter the stage 2 design phase once it will begin next year sometime, probably in the beginning. The last plane of action that we are working on is related to the way for the entire plan of activity to be sustained. So we have discussions or contacts with government officials and others to understand in which way the financial contributions that are required for a program like this can be obtained. Large investments can be necessary, and of course this requires some action, some planning, and some activities that are needed to arrive at the point where this can be decided. the few ideas that we have been carrying in the discussions to start the negotiations with the consortia and the presentation of our activity have been based on the number of proposals that we have been designing. And these are discussed with them and are related mainly to the plane of design to cost and operation efficiency. So there are ways to calibrate the system, there are ways to manage all the logistical aspects involved with the operations, as well as others which are more related to the design part of the program. We have some particularly electronic technologies that we are very clever in managing, and we have been trying to discuss with them if there are possibilities for these technologies to be considered in the designs alternatives that they are considering these days. We also have some ideas on the research side which can eventually lead to use the satellite constellations to help calibration of the system. And on these research ideas, we have been talking directly with the SKA organization in Manchester, because we are trying to see if a research program can be put together. At the moment, the discussion is still in the initial phase. A few ideas have been discussed with them, but we still need to perform more iterations, particularly because they want to be sure that the research topics we will address will fall inside the specifications list that they have today for the system. So in conclusion, this is an initiative that we are working on quite intensely these days, and we are very much committed to it, because we believe that for the industry, in particular for the Italian industry, it will be very important to be part of these designs and of the program of construction these very important systems. So, thank you very much.
Thank you very much. Questions or comments or curiosities? You're welcome to ask during the coffee break. Then we thank the speaker again, and we reconvene at 4:30.